Hello, I'm Sehoon Oh from Digis. Today's talk is about how to build a high-performance interaction force control utilizing multiple sensors. So this is the outline of today's talk. First, I will talk about the significance of the interaction force control in recent robotics engineering. Then the type of interaction controls as well as the actuators utilized for the interaction control is categorized. 4 types of interactions and 3 types of interactive actuator systems are explained. Each interactive actuator type has its own limitation, which will be introduced in this talk. And lastly, different types of interactive actuators are integrated to provide enhanced interactive force measurement, transmission force observer, and reduced order multi-sensor based force observer will be introduced in this talk as the example of this high-performance interaction force measurement based on multiple sensors. So as you know, recently the applications of the robots are expanded from manufacturing industry to various fields, where the interactive force control plays an important role. Collaborative robot, biped robot, or quadruped robot, and even wearable robot. They all require high-performance interaction force control. So they need to measure the interaction force between robot and humans or the environment to provide better service. This means that we need to analyze the details of the interaction force control and find out the issues in interaction force control. To that end, I categorize the interactions between the robot and human into 4 types. In type 1, the robot moves actively and the human grabs it or is attached to the robot to make passive motion following the robot. The examples of this type are passive exercises for rehabilitation. Type 2 is for power augmentation or power assistance, where the human leads the motion actively while the robot senses the motion and assists it. In type 3, the human also leads the motion while the robot follows human's motion passively without generating any interactive force. This is when human teaches or guides the robot or when the robot measures human's motion. In type 4, the robot generates resistive force against human's active motion. This is for sports training and resistive exercise. Notice that these different types interaction force control cases require different interactions. For type 2 and type 3, we need compliant interaction, which means that the robot should be able to provide enough compliance, while for type 1 and 4, the robot needs to be very rigid. This wide spectrum of interaction type is not easy to realize using conventional interaction force control technologies. There are various issues to be addressed to achieve these interactions. The most significant problem of the interaction force control is caused by the asymmetric characteristic of the transmission gear. As Professor Fujimoto investigated in this good paper, the efficiency of the gears are usually different in the forward direction and the backward direction, which means that the dynamics of robot appears in a different way for the interaction force control. You can design controller of the robot for tracking the desired motion, measuring the angles of the motor. But in the interaction force control cannot be realized in that way. You need to know the actual interaction force beyond the transmission gear. So two remedies are widely adopted for this issue. One is to utilize a direct drive or low gear ratio actuation system, and the other is to utilize additional sensor that can measure the interactive force. The methodologies to realize the interactive force control can be categorized into three types based on how to measure the interactive force. Type 1 is to utilize force sensors such as the FT sensors and load cell. This type is advantageous that you don't need to change your actuation system too much, and you only need to attach the force sensor at the end point where the interactive force measurement is necessary. Moreover, the whole rigidity of the actuation system will be maintained, which is necessary when you need high bandwidth position control. However, there are noise issues in most of force sensor, and it will deteriorate the performance of the interaction control. And the second type is to utilize elasticity to measure the interactive force. Series elastic actuator is the most well-known actuator system of this type. This type is advantageous when you need to realize compliant and very sensitive interaction. However, it is well known that this type of approach has limitation when it needs to realize high stiffness. Type 3 is to utilize motor angle measurement to measure the interaction force, utilizing the dynamic model of actuation system. This approach has advantage that it does not need additional sensors, and the rigidity of the actuation system is still high, which means that high position control bandwidth can be kept. But the problem is that the force estimation is not accurate enough, particularly when the transmission has no backdrivability and high friction. Therefore, different type of interaction control system is applied based on the required compliance and sensitivity. Type 2 system, such as SCA, is utilized when high sensitivity and compliant actuation are required, while Type 1 and 3 system is adopted when high stiffness is necessary. In other words, the compliance and the sensitivity are the key characteristics to understand and analyze the interaction control. Okay, with the proposed understanding and categorization of the interaction force control system, I will explain the characteristic of each type one by one. First, the force control system with the force sensor. This system consists of the motor, the transmission, the force sensor, and the load. This figure shows one example of force sensor using force control system, where this is the motor connected to the ball screw. The force sensor is attached between the end of ball screw and the load, which is the upper plate of this stage. This structure can be illustrated using this diagram, which shows the component of this system and the relationship among them. The motor motion is transmitted to the load through the transmission and the force sensor. The interaction force from the load is transmitted to the motor side also through the transmission. The force sensor can measure this transmitted force between the transmission and the load. This is the experimental demonstration of the interaction force control. The interaction force control is controlled to be zero to realize the compliant motion here. And this is the compliance this force control system can achieve. As I mentioned earlier, the user still feels some impedance as this type force control has the limitation when it comes to compliance force control. Series elastic actuator is one example of the second type interaction control actuator, which has the spring or elasticity to measure the interaction force. Notice that SCA utilizes encoder to measure the force, unlike the general force sensor. The structure of SCA can be illustrated as this. The motor torque is transmitted to the spring through the transmission gear, generating the deformation of the spring. This spring generates the force proportional to the deformation based on the Hooke's law, and that spring force is transmitted to the load. This spring force is measured by the spring deformation and the spring stiffness. This video shows the working principle of SEA, which consists of a motor and the planetary gear and the torsional spring to measure the spring force. Notice that additional encoder is attached to measure the spring deformation. In this way, SEA can generate the motion and torque utilizing motor and the gear, while it can measure the reaction force against the external force by measuring and controlling spring deformation. This is a parallel robot driven by 3-series elastic actuator. As you can see here, it can generate large force enough to support human's weight, while it can generate very compliant interaction. Even though the characteristics of type 1 actuator and type 2 actuator are different, the structure of these two interaction force control systems are similar. They have a motor and transmission gear, and the force at the gear is transmitted to the load through the force sensing mechanism. In type 1, force sensing mechanism is the force sensor, and it is the spring in type 2. Taking this structure into consideration, the general dynamic structure of the interaction force control can be derived as this. It consists of the motor dynamics, the transmission, force sensing mechanism, and the load. The motor torque is applied here, and the interactive force is applied here. The force measurement is the force here that is transmitted to the load and the motor. Type 3 interaction control is based on this understanding of the dynamics. As you can see here, the interactive force affects the motor torque as an external force or maybe disturbance. Making use of this point, external force can be measured, estimated by utilizing disturbance observer, or also known as a reaction force observer or residual-based torque estimator. As long as transmission is backdrivable and the friction is measured in advance, this type of interaction force observer estimates force accurately, as shown here. This is the demonstration of type 3 interaction force control. The door, which is driven by electric motor, is controlled to generate stiff and compliant interaction force. It can be verified that the interaction of the door with human can be controlled without utilizing any force sensor. However, each force control approach has its own drawbacks. Mostly, measurements by each sensing mechanism has limitations. For example, force sensor is very subjective to the noise and offset, and it is not easy to realize high sensitive force control, while spring of SEA has the hysteresis issue. To overcome these limitations, multiple sensors can be utilized at the same time. In this talk, our recent developments are explained on this multiple sensor based force estimation. One is transmission force observer, which combines type 2 and type 3, and the other is reduced order multiple sensor-based force observer, which combines type 1 and type 3. This graph shows the limitations of the force measurement in SEA. This x-axis here is the spring deformation, and y-axis is the actual torque measurement by the external torque sensor. Theoretically, the spring torque is considered to be proportional to the spring deformation, which is relatively true when the spring stiffness is low, as shown in the green and blue line. So this low stiffness case, the linearity can be observed like this. However, hysteresis of the spring leads to the discrepancy between the actual spring torque and the theoretical spring torque, as shown in the red and black line. And this figure shows more clear discrepancy, which compares the force measured by external force sensor and the force estimated by the spring deformation. So this is a very significant problem when SEA force information is fed back to the controller with high gain. So this hysteresis can even deteriorate the feedback stability, which explains why the performance of the force control is limited when high stiffness spring is utilized. So this explains the force measurement of SEA as the block diagram. So the difference between the motor angle, the load angle corresponds to the spring deformation, and this spring torque is calculated by multiplying the known spring stiffness. But this measurement can include some error when there is non-linearity, such as hysteresis, shown here. The same spring torque can also be estimated utilizing force observer, which is type 3 approach. So this block shows the force observer based on motor dynamics. And the equation illustrates what this force observer measures. Even though this type 3 approach can estimate the spring torque tau s, it also has a limitation. The high frequency information of the spring torque is missing, as the observer includes this low pass filter. An additional disturbance other than the spring torque will be included. To overcome the drawbacks of two approaches, we combined two approaches in the complementary way. The spring deformation-based torque estimation is combined to the force observer torque estimation through the high-pass filter. So this integrated observer, which is named transmission force observer, can estimate the spring force utilizing both spring, the motor encoder, and the spring deformation. So in the low frequency area, the spring force is estimated mainly based on the force observer, while the force is estimated by the spring deformation in the high frequency area. So this and the switching frequency can be set by the cutoff frequency of the low pass filter and high pass filter here. These results show the effectiveness of the proposed TFOB. Different magnitude external force are applied from small force to large force, and the force is applied sinusoidal way with a slow frequency. And this x-axis is the force estimation result with three different approaches, which are the spring deformation based approach, the blue line, and the force observer approach, the red line, and the TFO approach, orange line. The y-axis is the force measurement result by the external sensors. So if the plots are linear as this dashed line, it can be said that the force estimation results are very as accurate as the external force sensor. And the blue line, which is the force estimation by the spring deformation, shows very poor result, particularly when the forces are small. Meanwhile, the red line, which is the force observer result, shows bad result when large forces are added. So among these approaches, TFOB result, which is the orange line, shows the best estimation performance, which also can be verified by checking the error. This is another experimental result when fast interaction force are added with 3 Hz frequency. Similarly to the previous result, the spring deformation-based result shows poor estimation result when small forces are added. And the estimation performance of force observer becomes even worse with this fast force application. This is due to the low-pass filter characteristic embedded in the force observer. In this experiment also, TFOB always shows the best estimation performance among all 3 approaches. This video shows the estimation performance of the TFOB. And the result of TFOB is described as the red line here. And this shows good estimation performance which overcomes the conventional estimation approach. Particularly, the conventional one leaves this offset, while the proposed TFOB can go back when there is no force applied. So then I will explain the next approach to combine the force sensor measurement and encoder-based force estimation, which we named it reduced order multiple sensor-based force observer. So this is the structure of general force control system with force sensor, which can be modeled as this diagram, which is very similar to the structure of SCEA. This is the transmission force to be measured by the force sensor, which affects the motor side and the load side at the same time. The force measurement, however, is affected by the offset and the noise, in addition to the actual force to be measured. This force sensor measurement can be modeled utilizing the state space description. So the transmitted force F is modeled as a state as shown in here. And the F, because F can be measured, it appears in the output equation, as well as the motor angle theta. We also want to model the offset, that affects the force measurement. So we want to model the sensor offset using a random walk model shown here. So we proposed a new augmented state space model, which is the stochastic model of the force measurement system here. So we will utilize this model to design a novel force observer, which includes system noise omega and the offset noise omega off, as well as the measurement noise theta n and fn. Utilizing this state space model, state observer can be designed. First, a full order Kalman filter is designed as shown in this slide. The state is defined using including motor angle, angular velocity, transmitted force, and force measurement offset. Other type of linear observer can be designed. However, we designed Kalman filter with the covariance setting shown here. As you can see here, the number of the covariances to be set in this Kalman filter design is very many, which is sometimes very hard to set. So we came up with simpler design utilizing the reduced order observer design. This is the reduced order observer design for this multiple sensor based force observer. As there are states that can be directly measurable by the sensor, the full state is divided into the measurable state and non-measurable state. The transformation matrix can be derived utilizing C matrix is shown here, and the new state are designed utilizing this transformation matrix. The reduced order observer estimate only this unmeasurable state, and which means the reduced order observer is second order observer. As the result, the observer gain to be designed is reduced from 4x4 matrix to this 2x2 matrix. Therefore, the number of covariance values to be set for the Kalman filter design also reduced as shown in here. Because the order of the observer is reduced, the observer structure also can be redesigned as the second order filter as shown here. So this filter formulation is helpful when investigating how the observer gain affects the observation performance. So two estimators are of interest in this paper, force estimator and offset estimator. So the formulation shows that this force and offset estimation utilize multiple sensors, force sensor and encoder, even motor torque information. The designed reduced order multiple sensor based force observer is applied to this force control system, and the specification of the system is shown here. Two force sensors are utilized. One is the force measurement to be utilized for the observer, and the other is a better and more expensive force sensor to check the accuracy. Three different experiments are conducted to check the effectiveness of the RMFOV. At first, we recorded force measurement as well as RMFOV estimate for an hour with no load attached at room temperature. The green line shows the force sensor measurement, which clearly shows the offset in it. However, the RMFOV, which is red line, can estimate this state accurately, leaving the force state at the true value. Then we apply heat to the force sensor up to 45 degrees to check the offset characteristic. This figure verifies that the offset is observed as an independent state, and the force observation is not affected by this offset, while the green line, which is the force sensor measurement, is affected by the offset. Also, we added a sudden perturbation to the force sensor and see the measurement result. The force sensor by itself cannot recover to the initial zero values, while the RMFOV can. The effectiveness of RMFOV is verified with more experimental results. In these experiments, the force control system generates forces interacting with a human. The motion during the force interaction is in three ways. During this static load condition, the force control system does not move but provide static force to the load. During slow load motion condition, motion of the system is relatively slow than the fast load motion condition. The motor velocity plotted in this second line compares the speed of the condition, where we can find difference among three types of the load. The result shows that the proposed RMFOV outperforms other measurement methodologies in all the cases. Now I'll conclude my talk. In this talk, the details of the force control system are discussed, focusing on the types of interaction control and the type of interaction force system. The force measurement mechanisms are categorized to the force sensor type and the spring deformation type and the motor type. It is also shown that the dynamics of this force control system can be formulated in a common way that consists of motor dynamics, the force measurement mechanism, and the load dynamics. And the limitations of each force sensor measurement mechanisms are explained, and the remedies to overcome the limitations are explained. TFOB and RMFOB are the observer algorithm that utilizes multiple sensors combining this type to provide better force estimation. The interaction force control performance will be enhanced by utilizing these observers, and we are working on the optimal controller design utilizing these algorithms. While closing this talk, I want to thank two of my co-workers, Professor Lee and Mr. Samuel. Thank you for your listening.